Hi, I'm Joe James. I have a master's degree in computer science, and I'm a software engineer in Silicon Valley. And in this course, we're going to learn about data structures in Python. You might be wondering, well, why should I care about data structures in Python? Let's imagine for a second that you're a carpenter. You wouldn't try to pound in a nail with a screwdriver. That just doesn't make sense. Carpenters know you can't do that. You also wouldn't try to drive in a screw with a pair of pliers. So carpenters know that for every task, there's a best tool for the job. And that's why carpenters carry around a tool belt full of tools, and those tools are specialized for different tasks. And that's exactly what you're going to do when you master data structures in Python. Data structures are your tool belt. For each task you face as a programmer, you're going to know exactly which data structure to use and how to use it. You're going to save time, write better code, and do it more efficiently. So in this course, we're going to learn about Python's built-in data structures, strings, lists, tuples, sets, and dictionaries. Then we're going to continue to learn about queues, stacks, and heaps. We're also going to learn about linked lists. Then we're going to cover binary search trees and graphs. You're going to learn how to use these data structures, how to implement them in Python, and you're going to learn the strengths and weaknesses of each of these data structures. So let's look at some of the code. First, we'll look at sequence types, string, list, and tuple. So I put a link here to the documentation. This is the official Python documentation. I encourage you to check that out. If you have any questions or you want more detail on any of these items, just look at the documentation link here. So first is indexing. We can access any item in a sequence by using its index. We put that index inside square brackets, and indexing starts with 0. The first element is always 0. So the fourth element is going to be index 3. So here we have a string frog. It has 4 letters in it. If we want the fourth element, which is G, we print out x of 3. That gives us the G, as you can see in the output here. If we have a list of pig, cow, and horse, these are strings, we can print out x of 1, and that's going to give us cow. And again, it's just square brackets. And a tuple with 4 names in it, and if we want the very first name, we print out x of 0 with the 0 in square brackets, and that gives us Kevin. So that's indexing. Now let's look at slicing. We can slice out substrings, sublists, or subtuples using indexes. So the way indexing works is you put inside the square brackets separated by colons 3 possible parameters. So we can put a start, an end plus 1, and a step. And I'll show you what each of these means. So let's just use a string for this example. Computer, the word computer. Again, the C is index 0. So here we're going to print out x of 1 to 4. So since we didn't put a third parameter, that means the step is assumed to be 1. That's the default step. So when we put 1, that means the O. And that is inclusive. The from is, or the start is always inclusive. The end is non-inclusive. So if we look at item number 4, that's the U, that's the 5th item. It's non-inclusive. So it's really just going to get OMP for us. And when we look at the result, it prints out OMP. Now here's an example using a step. So we print out x of 1 to 6. Again, we're going to start at the O because the 1 is inclusive. And we're going to go up to 6, which is the E, but it's non-inclusive. And we're going to do it in a step of 2. So in other words, we're going to get the O, the P, and the T. And that's what we print out, OPT. So it takes every other item when we have a step of 2. Next, we're going to not put a end plus 1. We're just going to leave an open colon there. And what happens is when we put the open colon, 3 colon nothing, basically the default is end of string. So everything from the third item on. So here the third item is P, because we start counting at 0. The third item is P, and we get everything from P onward, P-U-T-E-R. So if you don't know how long a string is, or you just want to get all of the remaining elements, skip the first three items or something, you use an open colon. Next, we're not going to declare a start. So we can skip the start by just putting colon 5. So in other words, our default is we're going to start from the beginning of the string. We're going to get up to the sixth item because the 5 is non-inclusive. So COMPU. And you can see our result here is COMPU. So you can see if you don't declare a start, the start defaults to the beginning. And if you don't declare an end, the end defaults to the end. And if you don't declare a step, the step defaults to 1. So that's basically what's happening here. Let's look at a negative index. So if we print out just a negative index, -1, that counts from the right side of the string. So here we want the very last item in the string. We put -1, we get the R, the last element. And then here we get the last 3 items. So we put a -3 as the from and to the end of the string. So that gives us TER, that gives us the last 3 elements. And then if we want to get everything except the last 2 elements of the string, we leave the start blank, so we get everything from the beginning up until the last 2 items. So that is how slicing works, and it works exactly the same as we just covered for this string example. It works exactly the same on lists and tuples. Now let's look at adding and concatenating. So we can combine 2 sequences of the same type using the plus sign. Let's look at a string example first. We want to combine horse and shoe, and we just print X. So we see the result is horseshoe. If we have 2 separate lists and we want to merge those 2 lists together, we can use a plus sign. And when we print that, we get a single list with 3 elements in it. And in the case of tuples, if we have 2 separate tuples, and we print the result, we get a single tuple with 4 elements in it. Now it's important to note here, for the second one to be considered a tuple, we have to include a comma here. If we don't have that comma, it's just a string in parentheses. If we include this comma, that tells Python that this is actually a tuple. We can use the multiplying function to multiply a sequence using the asterisk. In a string example, if we want to print bug 3 times, we just do bug times 3 and then print. And you can see the result here is bug, bug, bug. And the same with a list. We have a list 8, 5, and we want to multiply that by 3. What we get is 8, 5, 8, 5, 8, 5. So we're not actually multiplying the elements by 3, we're multiplying the list by 3. And then the same with tuple. We can multiply a tuple by 3, and then we get basically a triplicate of that tuple. Now let's look at testing membership. We can test whether an item is in or not in a sequence. These are really easy, it's almost English keywords in Python. They made it so simple. So with a string, let's say we have a string called bug and we want to check if the letter U is in our string. We just say U in X, and that's going to give us a Boolean result, true or false. In this case, U is in X, so it returns true. And now we have a list, pig, cow, and horse. If we print cow not in Y, it's going to print false because cow is in Y. And for a tuple example, we have a tuple here with 4 names. And if we print one of those names in Z, we get true because it is in Z. So it's really easy to check membership using in or not in. If we want to iterate through the items in a sequence, we can say for item in X. An item can be any variable name you want. It can be for number in X or whatever you like. Here I just used a variable name item. Print item. If you want both the index and the item, here we have a list with 7, 8, and 3 in it. We say index, comma, item in enumerate X. The enumerate is going to return both an index and an item. So actually, again, these variable names are arbitrary. The first one is going to be the index. The second one is going to be the item itself. So you can name them whatever variable name you like, but you can get both the index and the item using the enumerate function. And then we have access to both the index and the item, as you can see the results. If you want to get the count or the number of items in a sequence, you can just use the len function. So in the string example, we have bug. We get len of X 3. This list, we have 3 items in the list, so we print len of Y, we get 3. In our tuple, the len of Z is 4. To find the minimum item, Python checks this lexicographically, which means the smallest on the ASCII scale. So you can use the minimum function on either alpha or numeric types, but you cannot mix alpha and numeric types into a list or a tuple. You'll get an error. So here in our string example, we print the min of x. We get the smallest letter, which is b. And in the list, we print the minimum of y, which is cow, because it basically is going to compare the first letter first, and C, it comes first alphabetically. And the same with the tuple, we print the one that comes first alphabetically, and that's Craig. So that's the min. The maximum item in a sequence, again, lexicographically, and it can be done alpha or numerically, but not both. So with bug, the maximum is U, and with pig, cow, and horse, we see that pig actually comes last alphabetically, and in our tuple example, in is the last letter alphabetically. We can find the sum of items in a sequence. They have to be numeric. So if you mix in other items that are non-numeric, let's say strings or something, it's going to give you an error. So in the case of a string, we throw a string in here and we find that we print sum, you're just going to get an error. But if we have a list of numbers and we print the sum of that list, you can see we get 27. You can also do slicing. You can combine slicing to get a sum of part of the list. So if here we want to just get the last two numbers, 8 and 12, we can do -2 onward, and that gives us 20 because we're adding 8 and 12 only. And for the tuple, we have another tuple z with 4 items in it, and we add those together, we get 80. Sorting returns a new list of items in sorted order, but it returns it as a list. So here we have a string, bug. We print the sorted version of x, and what we get back is the letters basically separated and sorted as a list, elements of a list. Our list example, it sees that these are strings, it puts them in sorted order, and it returns the list in sorted order. And it's important to understand that this does not change the original list. The sorted function is not an in-place sort. It returns a new list with the sort result. And our tuple example, we have 4 names here, and we put those in sorted order, and we get Craig, Jenny, Kevin, and Nicholas. So let's say you don't want to sort by the first letter, though. You want to sort instead by the second letter. Well, you can use a lambda function to do that. I'm not going to cover lambda functions in detail in this video, but I want to make you aware that you can sort stuff either by reverse order or using some other parameter. And we do that using key equals some lambda function. And here for each item, k, you can use as an arbitrary variable named k, we're going to take the 1th item, which is the second letter. So here it's going to be E, I, E, and R. And we're going to put those in sorted order based on the second letter. And we can see those with the second letter in sorted order. If we want to get the count of items in a sequence, we can use the count function. And here we have the word hippo in a string. We're going to count the number of times the letter P appears in hippo, and we can see that the result is 2. Here I added the word cow to the list twice, so if we get the count of the word cow, we see that that also is 2. And here we just get the word count of Kevin in this list, and we can see that it's 1. And we can get the index of an item by passing in that item and asking for the index of it. And what it's going to give us is the index of the first occurrence of that item. So in the case of hippo, if we're looking for P, it's going to give us, let's see, H is 0, I is 1, the first P is 2. So we can see the result we get is 2. It stops looking after it finds the first item that matches in the sequence. And our list example, we have cow. We have 2 cows in here, and we're going to get the index of cow, and we're going to get 1 as a return value. And then for the tuple, we get the index of Jenny, and we can see that's 0, 1, 2. So unpacking of items in a sequence, we can unpack those into a number of variables. It's important that our number of variables exactly matches the length of that list or string, because if not, we're going to get an error. So here we have a list x equals pig, cow, and horse, and if we want to unpack those and assign each of these values to its own variable, we can say a, comma b, comma c equals x. And then that's basically going to put these in order, assigning them to a, b, and c. So when we print out a, b, and c now, these are each separate variables: pig, cow, and horse. So that's called unpacking. In the next lecture, we'll learn more detailed features of lists, tuples, sets, and dictionaries. So now let's dig into some of the specifics of lists, tuples, sets, and dictionaries. Again, as a recap, lists are the most general purpose data structure in Python. You're going to use these for almost everything in Python. I should say a lot of stuff. And lists can grow and shrink in size as needed, so you can continue adding items to them or deleting items from them, and the size of the list will shrink accordingly automatically. Python does that for you. And lists are a sequence type, so all of the sequence functions that we covered above are all useful for lists, and they're also sortable. A lot of data structures are not sortable. Lists are. That makes them useful for sorting data. So let's look at some of the constructors for lists. How do we create a new list? So there are a few different ways of doing this. One, we can create an empty list by just saying x equals list and then parentheses. That calls the list constructor with no parameters, and it gives us a new empty list. And another way to do it is, this is probably the most common way, is to pass in the items we want in that list inside square brackets. These square brackets, we can separate each item with a comma. We can pass in, here we have multiple different data types. We have strings, we have integers, and floating point values all in the same list. And that's one nice thing about the versatility of lists you can see here. We can also create a tuple, which we'll cover tuple constructors in a minute, but as we create a new tuple, and we can pass that tuple into the list constructor just by putting it inside the parentheses in the list constructor, and that'll create a new list and assign it to Z. And lastly, we can use list comprehensions. I'm going to have another section on list comprehensions in a few minutes, so I just wanted to give you a little teaser of what you can do with list comprehensions to create new lists with sets of values. So here we're going to create a new list called A, and we put square brackets, and basically inside of that is a for loop and the range function. So we can say m for m in range 8. That's going to count from 0 to 7, and for each value m, it's going to assign m to the list. So here we get a new list with values 0 through 7 in it. And then if we want to do something more fancy, here's just a taste of it. I in range 10, so we're going to count 0 through 9, and we're only going to take the ones that are greater than 4. If I is greater than 4, then it'll pass I squared into the list. So here we get 5 through 9 squared into this new list. So that's a taste of what you can do with list comprehensions to create a new list using a for loop and the range function. You can also add if to filter items, and you can do whatever you want to the items that you're iterating. Now let's take a look at the delete function. If we want to delete a single item from a list, or we want to delete the entire list, we can do that using del. Here we have a list called X, and we have 5386 in it. And if we want to delete the 1th item, which is the 3, and we can just pass in the 1 in the square brackets, the index of that item, del x of 1. That deletes the 1th item, the 3, and we can see the new list there. And if we want to delete the entire list, we just say del x. Next, the append function. If we want to add an item onto the list, this is going to add it to the tail end of the list. We create a new list, 5386, and we do x.append. And then we pass in that 7 as an argument, and we can append 7 to the tail of the list. Extend basically is similar to the plus function that we used up above. We're basically combining two separate lists into one list. So here we have x equals 5386, y equals 1213, and we can extend x with y. And then we print out the new x, and you can see we have all 6 items in it. We could also have used the plus for that. So insert, we can insert an item at a given index in a list. Here we have the same list we used above, and we insert at the 1th position the item 7. So here we can see the result is 57386. This is the position or the index we want to insert it at, and this is the item we want to insert. And then we can see here that you can not only insert an integer or a floating point value, you can insert a list into a list as an item. We have a list here with A and M in it as 2 items, and then we print out the revised list and we see that the second item or the 1th item in the list is another list with A and M in it. So that's the insert function. Let's take a look at pop. Pop basically pops off the last item from the list and it returns that item. So you can use that item if you want to. You don't have to, but you are basically shrinking your list by 1 item. So here we have 5386. As we pop off 1 item using x.pop, that pops off the last item as 6. We didn't assign it to anything or do anything with it, but we can see the new list is just 538. Here we print x.pop and it pops off the 8, the last item on the list now. And we print that. So we can see that the return value is 8 when we do x.pop. Remove, we can remove the first instance of an item. So if there are multiple instances of an item, Python is going to start searching at the beginning of the list until it finds that item that matches. It's going to stop searching and it's going to remove that item. So here we have multiple 3s in this list. We're just going to remove the very first one. So if we do x.remove 3, we can see the revised list is without the first 3. Reverse function can reverse the order of a list. It's an in-place reverse, which means that it changes the original list. The original list is no longer the same as it was. So here we have an original list of x equals 5386, and then we apply reverse to it. It's not putting these in sorted order, it's simply reversing the order of the items. So we get 6835 as the reversed list. And then we can apply the sort function to it, which is also an in-place sort. You should note that we can use sorted of x. These are Python functions. There are 2 different ones, and they're a little bit confusing here. Sort is an in-place sort. Sorted returns a new list, so it's not an in-place sort. So here using the x.sort function, we don't pass anything in as a parameter to the sort function. We're applying the sort function to the x, which is what's calling the sort function. And we can see that we put these items in sorted order. And then if you want to do a reverse sort, we can pass into the sort function a parameter called reverse equals true. And that will give you a descending sort. So we get 8653 if we try and use reverse equals true. And again, this is the same parameter that you would use in the sorted function if you wanted to reverse sort using sorted function. But this one is an in-place sort.
As you can see, Python lists are a really powerful data structure and they have a lot of built-in functions and features. But unless you want to become the carpenter who tries to turn every problem into a nail by pounding on it with a hammer, let's continue on in the course and learn other data structures and see what they can be used for.
So let's take a closer look at tuples. Just to recap, we said that tuples are immutable. That means they can't be changed, and you can't add items to the tuple once it's created. They are useful for fixed data. If you're going to have a lot of changes to your data, then you should use lists. They are useful for fixed data. They're much faster for finding items than a list is. And these are sequence types, which means that all of the above functions are still going to work. So you can use all of those sequence functions that we've used above on tuples. So let's take a look at some of the constructors for tuples. How to create a new tuple? There are a few different ways of doing this. The tuple uses the parentheses as its constructor. So here we can create an empty new tuple using x equals parentheses, empty parentheses. Or if we want to pass in items, 1, 2, 3. The parentheses are actually optional, so even when you take the parentheses away, 1, 2, 3 separated by commas, Python knows that this is a tuple.
Now if you want a tuple of just one item, you still have to put the comma. That comma tells Python that this is a one item tuple and not just an integer. And then you can see that we print here x and the type of x, and we get a tuple with just the 2 in it, and the class is a tuple. Now let's create list1 equals 246. This is a list with 3 items in it. We pass that list into the tuple constructor, and it creates a tuple called x. So here as we print out x, which is that tuple 246, you can now see that it doesn't have square brackets. It has the parentheses around it because it's a tuple. And we print out the type of x, and it's a class tuple. So there are several different ways there to create tuples. Tuples, again, are immutable. However, this may be a little confusing, so pay attention. Member objects may be mutable. If you have a list as one of the items inside a tuple, you can make changes to that list. You can add or delete items from that list. You can change the items in the list. So let's take a look at what we mean here. If we have a tuple with 1, 2, 3 in it, and then we try to delete the 1th item, which is the 2, that's going to fail. That's going to give us an error in Python. If we try to change the value of the 2 to 8, that also fails. We cannot change the value of the 2. So it looks like the tuple is totally immutable and unchangeable. And we get 1, 2, 3. So even if you try those, you're just going to get an error. But look at this. If we assign a list, a 2-item list, as the 0th item in this tuple, well, that list it's mutable. So we can change or drop items off of this list if we want. So here we're going to pass in 2 indices. The 0 tells Python that, yeah, we want the 0th item of tuple y, which is this list with 1 and 2 in it. And in that list, we want the 1th item, which is the 2. And that's what we're going to delete. So we're basically deleting this 2 from this list. And then we're going to print out y, and we can see that the result is we get a single item list with the 1 and a 3. So we were able to edit this list with the 1 and 2. We're able to drop items off of that list. And then if we want to add items to the tuple, we cannot just add or append. However, we can use this concatenation function where we do y plus equals an additional tuple, and it will merge the 2 tuples into 1. So here again, you need the comma to tell Python that this is a tuple and not just an integer. It's a 1-item tuple. So if we do y plus equals 4, we can see that the 4 is added on to our original tuple y. So concatenating will work. Now let's look at sets. Sets store non-duplicate items. So unique items are really what sets are ideal for. You get very fast access compared to lists. And the reason why is when you iterate through a list looking for an item, the only way to do it is to start at the beginning and look at every single item and do a comparison. So if you have 1 billion items in that list, you're going to do you may have to do 1 billion comparisons to find that item. But in a set, it hashes that item. So it can find it instantly using the hash. It has much faster access than lists. So especially for very large data sets, it has much faster access to items than lists. It's great for checking membership. The set is also great for doing math set operations, things like union and intersection. And keep in mind that sets are unordered, which means you cannot sort a set. So let's take a look at the constructors for a set. Here are a few different ways to create a new set. We can use these curly braces, and you'll see here as we pass in 3535, we've got some duplicates there. What Python does is it filters out the dupes and gives us a set with just 3 and 5 in it. And if we create a new empty set, we can just use the set constructor with parentheses, and then when we print out y, you can see we get an empty set. If we want, we can also pass in a list. Here we have 2, 3, 4, and we call the set constructor using the parentheses and passing our set as a parameter. And we get a new set z, and then when we print that out, we get 2, 3, 4 as a set. So that's a few different ways to create sets. Some of the set operations you can use. you can add an item to a set by using x.add. So here we add a 7 to this list of 3, 8, 5, and then we remove a 3 using x.remove. So you can see the result here is that after you add the 7, you get the 4 item list, and when you delete the 3, you get back down to 8, 5, and 7. So add and remove both work for sets. And then if you want to get the length of a set, you just use len. Checking membership, we use in or not in. So if we want to check if 5 is in the set, we just do 5 in x or 5 not in x. And that's going to give us a Boolean return. Here we can see we got true for 5 in x. And then we can also pop a random item. Bear in mind the set is not ordered. So we don't know which item we're going to get. We're going to get a random item off the set. And then here, actually the pop function returns the item itself. And so we're printing out that item and the new list x. So here we can see the item it gave us is 8, and the new set is 5 and 7. And then if we want to delete all the items from a set and get an empty set back, we can do x.clear. Let's look at some of the mathematical set functions. So we said that we can do intersection and union, which are and or functions. So the intersection is done using an ampersand with 2 sets. And the union is done using the pipe or bar. So set 1, pipe, set 2. Symmetric difference, or exclusive or, in other words, in items that are in set 1 but not in set 2, or in set 2 but not in set 1. And the difference, we can just use a subtraction. So set 1 minus set 2 gives us the difference between those two. And then we can check if one set is a subset or fully contained in the other set using the less than or equal to or greater than or equal to for superset. So we have 2 different sets here, set 1 and set 2. And when we do the intersection, we can see that the intersection is 3. They both have this value 3. When we do the union, we get all the items that are in either set. So 1, 2, 3, 4, 5. So when we do exclusive or, using the up caret, we get 1, 2, 4, 5, which is all the items that are in one set or the other, but not in both. And then minus, we get 1 and 2. And then since neither set is a subset of the other set, both of these two return false. So those are some of the mathematical set operations you can do on sets. Now let's take a look at dictionaries. So first a recap on dictionaries. Dictionaries are key value pairs. So most programming languages have some equivalent of the Python dictionary. They don't always call it that. Some of them call it a hash map. Java calls it a hash map. Dictionaries are unordered. That means they cannot be sorted. They can be converted to a list and then sorted as a list, but they cannot be sorted as a dictionary. So some of the functions that we can do, how do we create new dictionaries? Let's take a look here at our constructors. So if we create a new dictionary using the curly braces, then we need to pass in members, key value pairs, separated by a colon, and then spaced out with commas. Okay, so here we have 3 key value pairs. The key is on the left, a colon, and then the value. And these are 3 different ways of creating exactly the same dictionary. So in the second example, we pass in a list of tuples. So the tuple contains 2 items. It has a string and separated by a comma, the floating point. So there are 3 tuples in a list passed into the dictionary constructor, which is in parentheses. And then the third one passes into the dictionary constructor. Notice that there are no quotation marks around the strings here. We just have pork equals 25.3, and Python knows that this is a string. So these are 3 different ways to create dictionaries in Python. They all do exactly the same thing. Some of the operations of dictionaries. Now we notice that shrimp is not in our dictionary. So if we want to add shrimp, we can say x of shrimp equals 38.2. In this case, there is no shrimp in the dictionary yet, so it's going to add a new key value pair for shrimp 38.2. If there already was a shrimp in the dictionary, then it would update the value to 38.2 for shrimp. it looks up this key and it will update the value for it. So this is add or update. And Python's not going to tell you if that was in there or not. If you want to check, you can check first, right? If shrimp in dictionary. But if you just do this x of shrimp equals 38.2, it's going to overwrite anything that was already in the dictionary for shrimp. If you want to delete an item, this is just del x of shrimp is going to delete shrimp from the dictionary. And then you can see that we print out the new dictionary. There's no shrimp in it. And if you want to get the length of the dictionary, you can print len of x. That'll tell you how many key value pairs are in the dictionary. And if you want to delete all the items from the dictionary, you can use x.clear. And lastly, to delete the entire dictionary and free up the memory that it's using, you can use del x. So to access keys and values in the dictionary, you can access these separately or you can access them together. So here are a few different ways of doing that. We have this dictionary Y with pork, beef, and chicken in it. Those are the keys, the strings, pork, beef, and chicken. So if we do y.keys, we get a list of pork, beef, and chicken. It dumps these out as a list. If we do y.values, it dumps these out as a list, the values, those floating point values. And if we do items, we can say print y.items. It's going to print out all the key value pairs. So here it prints them out as a list of tuples or key value pairs. To check membership in just the keys, you don't have to specify keys. You can if you want. You can say beef in y.keys, or you can just simply say beef in y, and that's going to check in y's keys only. It's not going to check in the values. If you want to check for membership only in the values, you can check clams in y.values. And all of these membership tests are going to have a Boolean return true or false. So to iterate a dictionary, keep in mind that these items are in random order, and you're not going to be able to iterate them in any kind of sorted order. Python's going to give them back to you in whatever order it wants. So for key in y, print key. That will give you all of the keys in the dictionary one at a time. And then you can get the value by saying y of key. So here you can see we printed out each key and its value. If we want to iterate with a separate variable for both the key and the value, sometimes this is helpful if you're doing a lot of operations inside the loop. You can put whatever variables you want. I used k, v as my variable names. And what you do is you iterate y.items. And then items returns a tuple, a two-item tuple of the key and the value, and it assigns them to whatever variable names you have here. So k and v in my case. So you can see the result here is the same. We iterate through the items, we print out both the key and the value. So that wraps up this video on built-in Python data structures. Now you should have a pretty good understanding of how to use Python's built-in data structures, strings, lists, tuples, sets, and dictionaries. Make sure you download the code and get some practice using it, because it's hands-on practice that's going to make you a good programmer. In the next section, we'll learn how to use list comprehensions to create new lists. Hi, I'm Joe. This chapter we're going to cover a pretty cool feature of Python called list comprehensions that enables you to create new lists of values using a comprehension, or basically sort of a for loop and iteration inside of a list creator. So our basic format is transform, sequence, and filter. So we can apply a filter to it if we want. And we put that inside square brackets. And the result is going to be assigned to a new list. So we're going to use the random module a little bit in this. You don't need that for all list comprehensions, but for one or two of my examples. So I'm going to import that. So we have a series of about 10 examples or something I'll show you, and they get increasingly more complex. So here we're going to just get values within a range. Typically in list comprehensions, you're going to use the range function. Here we just use range of 10. And you know the range function returns a sequence of numbers. In this case, it starts with 0, which is the default, and it goes up through 9 because the 10 is non-inclusive. So 0 through 9. And what we're going to add to this new list is x
for x in that range. So in this part, the first x, we could apply some sort of a transform or a function on that x if we wanted to, x squared, 2x, whatever we want. And then this is where we declare the variable, each x in this range. So the result is a series of values under 10. So 0 through 9, under 10 integers. Okay, so that's the simplest example of a list comprehension. Now let's look at some of the other more crazy stuff that you can do with list comprehensions. We could get all the squares if we want. I told you we could apply a transformation to the x if we want. So here we declare our variable as x as we iterate through under 10, which is this list we just created. Okay, so we don't necessarily have to use the range function. We can use any sequence here, which means we could use a list, we could use a tuple, a set, or even a string, or a range function. So x squared for x in under 10. So it's going to iterate through these. It's going to return the square of each one of them, and it's going to assign that to this new list called squares. And then we're going to print out squares. So you can see the result is 0 through 81, the squares of the previous list. Okay, let's see what else we can do. Get odd numbers using mod. Okay, so odds equals x for x in range 10. So here we're going to just basically iterate through 0 through 9. The variable we're going to use is called x, and we're going to send x to this odds list. But here, look, we apply a test, a condition. If x mod 2 is equal to 1, in other words, if it's odd. If x is odd, then we'll send it to this odds list. When we print it out, we see that we get 1, 3, 5, 7, and 9. Now let's get the multiples of 10. So we're going to use the range function again as our sequence, 0 through 9. And instead of adding x to the list, we're going to add x times 10. So this is not a whole lot different from the x squared we did. We get the multiples of 10, so 0 through 90. Now let's get all the numbers from a string. So we start out with a string named s that has a combination of letters and numbers in it. Maybe sometimes you want to filter out and delete all the numbers or whatever, but here what we're going to do is just create a new list with all those numbers. So nums equals x for x in s. In other words, we're going to iterate through the letters or characters in s, and we're going to test if each one is numeric. And if it is, then we're going to add it to this list. And then when we print out the list, we get a list, so I'm going to use this little join function to join the numbers into a single string. So we get 2073. In other words, we managed to grab all the integers in this string. So here we're going to get the index of a list item. And we're going to do that by using the enumerate function. So we iterate using enumerate names. This is a list. Names is a list, and we're going to enumerate. Enumerate returns both a key and a value for each item in the list. So we start out with Cosmo and 0, and then we get Pedro and 1, Anu and 2, right? So we're getting each name, we're getting the key and the value. Our test is if the value is equal to Anu. Okay, so that means here. Then the key is going to be equal to 2. And then what do we add to the list? Well, we add K. We add K, we add the key, we add 2. So at the end result here, we get a list with just a 2 in it, because that's the only one that passes this test. And then when we print out the 0th item in the list, of course it's a 2. It's a one-item list. And we can also delete an item from a list. Here we have a list of letters, actually a string. We start by iterating through the string A, B, C, D, E, F, converting it to a list of letters just by adding each letter in the string to a list. So now we have a list of A, B, C, D, E, F as individual letters. We shuffle those using this random function. So now we have shuffled letters A, B, C, D, E, F. And each one of them is basically a string object in the letters list. So we're going to create a new list that passes this test. A for A in letters if A is not C, right? In other words, every letter in this list except for uppercase C. So we're going to get A, B, D, E, F. And you see when we print them out, we get D, F, E, A, B, but we do not get C. So we get, yeah, that works pretty cool, huh? We basically filtered out the C wherever it is in the list. We don't know, but we filtered it out. That wraps up this lecture on list comprehensions. You can download this code from my GitHub site and test the code and run these examples. And I encourage you to use list comprehensions. These are really a useful tool in Python for creating lists.
In this section, we're going to learn how to use stacks, queues, and heaps. First, we'll cover the fundamentals of each of these data structures, what key operations each of them has, and then how you can implement them in Python. These are three very useful data structures. Let's start by learning about stacks. A stack is a last in, first out data structure. That's called LIFO. So what that means is that all the push and pop operations are to the top of the stack. They only affect the top item on the stack. The only way to access the bottom items on the stack, like in this diagram, item 1, is to first remove all of the items above it. We have a couple of different key operations here. Push allows us to push an item onto the top of the stack, and we use the pop command to pop an item off of the top of the stack. Some other stack operations are peek. Sometimes you might want to get an item off of the top of the stack without actually removing it. Let's say we need access to the top item, we want to know what it is, and we can use the peek command to see a copy of the top item without actually removing it from the stack. Or clear to remove all of the items from the stack and empty the stack out. There are a lot of different use cases for stacks. One very common use case is the command stack. All computer programs track each command that you execute. And most programs you use have the option of undoing the previous command. In order to do that, the program has to keep track of which commands you've executed in which order. So it does that using a stack. Each time you execute a command, it pushes that command onto the stack so that it has a record of it. And if you click the undo button, it's going to pop the last command off of the stack and it's going to reverse that command. So the command stack is used to execute the undo function in programming. Now let's take a look at how stacks can be implemented in code. We have the Python list, which makes a great foundational data structure to store the stack in. And actually Python gives us most of the functionality that we need to create a stack with the list. So the underlying data structure beyond our stack is going to be a Python list. Python gives us the append function, which we can use to push an item onto the stack, and it gives us the pop function, which we can use to remove an item from the stack. We're actually pushing items onto a list and popping them from a list. So here's one implementation. Using the Python list, we can create a new stack. My stack equals an empty list, and then we can push items onto the stack using append. As here we push 4, 7, 12, and 19 onto the stack. And then when we print out the stack, we can see 4 items. Now a little more test code here. When we pop an item off the stack, we can see that we get the 19 first. When we pop the second item off, we get the 12. So it's popping off the last item first, which is exactly what we want. So that's typical stack operation. However, it's using a Python list. Now if we wanted to write a wrapper class so that we can add some additional functionality to our stack, that's actually not that hard. So let's take a look at how that can be done. Here's a stack using a list as the underlying data structure, but using a wrapper class so that we can rename our functions as we like, and we can also add additional functions and features to our stack. So we'll start with a constructor, an init function, and this basically just has a new list. It creates an empty list just as we did before. The push is going to add an item, so we receive an item and we just use the append function to add that item onto the list.
what the user is going to see is he's pushing an item onto the stack, but what we're doing behind the scenes is appending that item to a list. Next, the pop function. First, we want to check if the list actually has items on the list. If the list is empty, we don't want to try a pop operation. If there's at least one item on the list, then we'll pop that item off and return it. The peek function allows us to just look at the top item on the list and return that item, but without taking it off. So here we return the top item on the list, but without removing it. And lastly, if someone wants to print out the stack or show all the items that are on the stack, what we're going to do is just show the string representation of the list. Now let's look at some test code and see how our stack works. My stack equals stack. And then we can push an item. We'll push a 1, we'll push a 3, and then when we print out the stack, we can see that, yeah, we have a 1 and a 3 on our stack. And when we pop an item off of the stack, we get the 3, which was the last item that we put on the stack. When we peek, we get the 1, which is the only item actually left on the stack, but peeking is going to give us the top item on the stack. If we pop another item, we get 1, and now the stack is empty. So if we try to pop another item, we get none. So basically all those key features of our stack are all working just fine. So this is how we can use a wrapper class to implement a stack in Python with an underlying data structure of the Python list. So the Python list is a very versatile data structure, and here we've used it to create a stack. Now let's take a look at queues. A queue is a FIFO, or first in, first out data structure. This is really intuitive because we see queues in every walk of life. Almost in everything you do on a daily basis, you encounter queues. Queues have two key functions. You enqueue an item by adding it to the end of the line. You dequeue an item means removing it from the front of the line. So some use cases for queues, just about everything you wait in line for. So bank tellers, placing an order at McDonald's or your favorite restaurant, DMV customer service, supermarket checkout, pretty much anything that has a line is what a queue is. And it's important to be able to model that in a computer program. So the queue data structure allows us to do that. Now let's take a look at how we can implement a queue in Python. It's actually pretty simple because Python already provides us a built-in library called the deque, or D-E-Q-U-E. That's a double-ended queue. That allows you to add and remove items from both ends of the queue. For our simple queue, we don't really need that functionality. We just want to be able to add items to one end of the queue and pop them off of the other. So we can use the append function to add items or push items onto our queue, and we can use pop left to remove items or pop items off of the queue. You can see the full documentation in Python here if you want to learn more about how double-ended queues work. So for basically just using a double-ended queue in Python as a single-ended queue, we can use from collections import deque. That's going to import our double-ended queue library, and then we'll create a new queue, myQueue, and that's going to be a double-ended queue object. And then we can append items or push items using the append function. So we can push a 5 and we can push a 10 onto the queue. And then when we print out the queue, we see that we have a double-ended queue with a 5 and a 10 on it. And then if we want to pop items off of the queue, we use pop left. And here we get the 5. That pops an item off of the tail end of the queue or the left end of the queue. So it's pretty easy to implement a queue in Python. This is obviously a common enough data structure that Python built in a library for it. Now, as a fun exercise for you, you may try writing a wrapper class for the double-ended queue to make a single-ended queue using push and pop, as we did similar for the stack. In this lecture, we're going to learn how to use max heaps. Now, implementation-wise, the underlying data structure is going to be a list. And the functions of a max heap are not a whole lot different from stack and queue. So I think you're going to be able to pick this up fairly easily. Now, when you look at this graphical representation of a max heap, though, it looks a lot like a tree. And I know we haven't covered trees yet. That's going to be covered in section 5. But bear with me, I think you're going to figure this out pretty easily. So, the one condition of a max heap is that every node is less than or equal to its parent. That's the key. So you'll see that 25 is the parent of 16 and 24, right? 25 has a left child and a right child, and it's greater than or equal to both of those. And then 16 is greater than or equal to both of its left and right children, and so on. So every node in the tree has to be less than or equal to its parent, and every parent node has to be greater than or equal to the nodes below it. So that is the core condition of a max heap. And the reason it's like this is so that we can instantly remove this max number anytime we want. Anytime we want to pop the top number off of the heap, we know that it's the highest number in that heap. So the highest number always rises to the top of the heap, and it can be instantly removed and used. So max heaps are fast. If you're familiar with Big O notation, you can insert or add an item to a max heap in Big O of log n time, which is extremely fast. And you can get an item, you can get the max item off of the top of the heap in Big O of 1 time, which is pretty much instantaneous. You can remove the max, or pop, in Big O of log n time. So the response time for a max heap is extremely fast. And that's why we use max heaps for some things. If you need to pop the maximum number off a heap, you can get it very quickly. Max heaps are easy to implement in Python using a list. Not as easy as the other 2 data structures we just covered, but not too hard. So I think you'll be able to follow this, but I'll warn you the code is a little bit longer and hairier than the previous 2 examples that we just covered. But I've already written all the code. All you have to do is just follow along with the explanation. So you can see that using a list, we have an index that corresponds, a list index that corresponds to each node, starting with 1 at the top, and then 2, 3 across, 4, 5, 6, 7 across on the next tier, and then on the next tier, 8, 9, 10. So it's a pretty easy indexing system that corresponds to these nodes on the tree. And then when you look at our list, how we put the items into the list, well look, 25 is at index 1, and then 16, and then 24. So look, we know that 16 is not greater than 24, but it looks like, wow, it's lower than node 3 here, or index 3. Why is that? Well, because our rule is that 16 has to be greater than everything below it on the tree, which it is. So our condition is met. This is a max heap. 16 does not have to be greater than 24. We didn't say greater than everything behind it on the list. No, on the tree. So this is a valid max heap. Okay? And that is how it is implemented in the list using these list indices. So we can instantly access any node in the tree or any node in the max heap. Now let's say we wanted to access the 5. We know that the index is 4. This is index number 4 for this 5 node. Now we can also access 5's parent, which is the 16. We simply divide the index by 2. So this 4 divided by 2 gives us the index of 5's parent node, which is 16. And if we want to access 5's children, it's the same thing. 5's left child is times 2 to get the index of 5's left child, 8. And then times 2 plus 1 gives us the index of 5's right child, 8 and 9. So if we take a given node at index 4, we can access his right and left child by times 2 and times 2 plus 1. And we can access 4's parent by just divide by 2. So it's pretty quick, easy operations to access the parent and children node in this tree. Now max heap operations, like I said, these are exactly the same operations that we just covered for stacks and cubes. So we want to be able to insert or push an item onto the heap. We want to be able to peek, find out what is the max item on the heap without popping it off. And then we want to be able to remove an item from the heap and return it, which is a pop operation. So the same 3 operations for heaps as we had for the previous 2 data structures. Let's look at how those work. So push. We can add a value to the end of the array, and then we float it up to its proper position. So let's look at an example. We want to push a 12 onto this heap. What we're going to do is put it at the very last spot in the array, which is here, right? And we have a spot for it. So in other words, it's going to be 11's right child. It's the last index in the array. And then we need to float it up to its proper position. Well, how do we do that? We need to compare 12 to 11. If 12 is greater, then these two will swap places. Yeah, it is greater. So we want the 12 and 11 to swap places. Now we need to compare 12 to its new parent, 16. Is 12 greater than 16? No, it's not. So there's no more swapping. 12 is already floated up to its proper position in the heap. So this is one of the key behind-the-scenes functions that we have to code, which is called float up or bubble up. When we add an item to the bottom of the tree, we need to be able to bubble it up to its correct position in the heap by comparing it to its parent nodes and then swapping. So we use that every time we do a push operation. Peek just returns the value at the top of the heap, okay, which is going to be heap of number 1, index number 1. And that's pretty straightforward. We don't really need to pop it off or anything. So we just get that item and return it. And in pop, first we're going to move this topmost item. We want to pop off the max, which we know is in index position 1. First we're going to swap it with the item in the last position. Then we're going to delete it from the heap, and then we're going to bubble down the item here to its proper position. So let's take a look at the example. So 11 is in the last position, 25 is the item we want to pop. So we're going to swap those two, 25 and 11 swap places. Now we can remove 25 from the heap without affecting the rest of the heap. It's in the last place, it doesn't affect anything else in the heap. Our next step is to bubble that 11 down to its correct position. So we compare 11 to 24. 11 is less than 24, so it needs to move down. Next, we're going to compare 11 to 19, and 11 is less than 19, so that's going to swap places. So we do some comparisons with the child nodes to move 11 down until there's either no further room to go down or it's not greater than any of its children nodes. So that's the operation for pop, and now we can just return the 25 that we pulled off. That's it. So those are the three key operations, and that's basically how they work in a nutshell. Now let's take a look at the code. Again, the underlying data structure we're using is a list. So you're going to see us using list indices throughout this program. Now the public functions we have here are push, peek, and pop. We're pretty familiar with those by this point. But we also have supporting private functions that we need for this heap. And we have basically a swap, a float up, and a bubble down. And we use those as internal utility functions. These are not part of the user interface. And then the string function is so that we can print the heap. So our constructor, when we create a new heap, we have the option of passing in a list of items that we want to add to the heap. If we don't pass in a list of items, then we'll get back an empty heap with just a 0 in it. So we put a 0 in the very first element because we don't use that. We start our elements at index number 1 for the max heap. If we pass in this list of items, we're basically going to iterate through those, add them one at a time to the end of the list, and then float it up to its proper position. That's the push operation. So essentially we're pushing them all one at a time. And when you look at the push method, it does exactly the same thing. It appends the data that you passed in to the end of the heap, and then it floats it up to its proper position in the heap. So that is the push operation, which is almost identical to the constructor if you pass in items. Now the peek operation doesn't do much. It only returns the top item on the heap. That's all. It doesn't take it off. There's no pop operation going on. It's just a peek. Now let's look at the pop operation. There are a few different cases here depending on how many items we have in the list. If the list has exactly 2 items, one of those is the 0 that we're not counting. We're not using that as part of our max heap. So if there are exactly 2 items, that means there's really just one item in our max heap. we'll pop off that number 1 item with index number 1 and we'll return it. We pass that into variable max, and then here at the end here we return max. If there are more than 2 items, then we're going to swap the maximum item, which is in position index 1, with the last item. So we get the last item in the list. We swap those two. We pop off the last item and assign it to this variable max. And then we bubble down the first item that we moved into the top position. So it's exactly what we just walked through in the slides. And then at the end we return the max. So that's how the pop operation works. And in our utility functions here, swap really just swaps 2 different items. We pass in 2 indices, we swap those 2 items in the list. Now the float up function is going to receive an index of the item that we want to float up, probably the very bottom item in the list initially. First we'll get the index of its parent. If it's already in the top position, then there's no floating up to do. It's already risen to the top. Otherwise, we're going to compare it to its parent, and if it's greater than its parent, then those two need to swap places. So we'll swap the positions of the item index passed in with its parent. Then we'll call the float up function recursively on the parent. So this will continue the float up function until the element reaches its proper position. Bubble down kind of does the opposite. It takes an element that's at the top of the list and it bubbles it down to its proper position. So we can pass in an index. We get the left child and the right child by multiplying the index by 2 and times 2 plus 1. And then we'll set the largest equal to index. We do a little comparison. If the item we're bubbling down is less than its left child, then we're going to swap positions with the left one. If the item we're bubbling down is less than the right child, then we're going to swap positions with the right child. So if there's any swapping to be done, at the very end here we check, do we need to swap? If so, we'll call this swap function on the item we're bubbling, the target item, with the larger of those two. And then we'll recursively call the bubble down function again on the same item that we just bubbled until it reaches its proper position. And our test code here, we don't have a whole lot of test code. We create a new max heap with 3 items in it. Obviously the 95 is the highest one and 21 is the second highest. We push a 10 on, and then we can see that our list now has, ignore the 0, really has 4 items in it. And when we pop one off, we get, of course, the 95. And when we peek at the next item, now that the 95 is gone, we can see that the 21 is the next item in the max heap. That is how a max heap works, and that's how you can implement it in Python. And by simply changing a few greater than or less than signs, you could change this to a min heap. Let's say you have a collection of items that you want to store, and you want to be able to iterate through them. So you want to be able to find an item in the list. You want to be able to insert an item, but you need very fast insertion speed, especially at the front of the list. You want to be able to insert new items at the front. You need to be able to remove items from the list. You also may want to iterate forward and backward through the list, or possibly even in a continuous circle through the list. So one possible storage solution for these requirements is a linked list. We're going to learn how to use linked lists and what they are, and we're going to learn a few different types of linked lists. A standard linked list, a bidirectional or doubly linked list, and also a circular linked list. We'll learn how those work, the major operations used with linked lists, and we're also going to go through, of course, how to code a linked list in Python. So let's take a look at how linked lists work. Every linked list is going to be composed of what we'll call nodes. You can call it whatever you want. In this video, we're just going to call each item in a linked list a node. You could store whatever data you want in a linked list. It could be a student node, it could be an employee node, whatever, it doesn't matter. But we're going to call it a node, and that's kind of the common nomenclature for the items in a linked list. Just call them nodes, and each node is connected to the next node, so it has a pointer to the next node. So those two things. It has a piece of data, which for us is just going to be an integer in this video, and it has a pointer to the next node. So those are the two key components of every node in the linked list. Now a linked list looks something like this. Each node has its own piece of data, and it also has a pointer to the next node. There can be any number of nodes. It's basically unlimited only by the amount of memory you have in your system. And the very last node here, you'll see, there's no next pointer. So we're going to store like a none there to indicate that there's no next node. That's the last node in the list. At the very front, we call that the root node. That's the first node in the list. So we need a pointer to point to the starting point for the list, and this is what we call the root. So we have a pointer to the root, and the operations that we need for each linked list, we need to be able to find data, we need to be able to add a piece of data, we need to be able to remove a piece of data from the linked list, and we need to be able to print the list somehow. So we're going to see how each of these operations works, and then we're going to see how to code it in Python. Now the attributes for a linked list, you have a pointer to that root node, and then we're also going to track the size of the linked list, so at any given time you could find out how many nodes are in the list. Let's look at the add operation. So here's our linked list. We have a pointer to the root. We want to add 10. That's our command. Let's add 10. So we first are going to create a new node with that data 10 in it. We don't have anything in the next pointer yet, but what we're going to do is we're going to point the next pointer to where the root is currently pointing. So the root currently points at this 5 node. We're going to put our next pointer for this new node pointing at the root node. And then we change our root to the 10. So we effectively inserted this new 10 node at the very beginning of the linked list. That's how we're going to do the insert operation. Next we want to try and remove a number. So let's try and remove 5. Obviously if we try to remove a number like 200 and it's not in this linked list, then we'll get back either a false or a none or sorry dude or an error or something. But if we have a number that's in the list and we want to try and remove that, so we're going to remove 5. First we need to find that 5. So we start at the root. We check if this is the number. No, it's not. Oh, is this the number? Yes, it is. Gee, so there's the node that we want to remove. Pretty easy to remove it. We take the previous node to this 5. We change the previous node's next pointer to 5's next pointer. In other words, see 5? The next node is 17. So we just change 5's previous node, which in this case is the root, the 10. We change that next pointer to where 5's next pointer goes. And so now effectively the 5 node is just completely cut out of the linked list. When we iterate through the linked list starting from the root, we're going to follow this path and we're never even going to know that the 5 is there. The 5 node still exists, but we don't have access to it anymore. It's effectively deleted from the linked list. So that's the remove operation. Now let's take a look at how to code a linked list in Python. We're going to start with the node class. We're going to use the same node class for 3 different types of linked lists that we cover in this section. So doubly linked lists and circular linked lists are going to use the same node class. And you'll see in the node class here that we have 3 attributes. We have a piece of data, we have a next node, and we have a previous node. Now in our standard linked list, we do not need the previous node. So we're just not going to use that attribute in the standard linked list, but it'll be there for us so that we can reuse the node class for the other 2 linked lists. And then we also have this string representation that gives us back essentially the data in parentheses. So that's what the string representation of a node is. So in the linked list we have 4 methods. We have an add, find, remove, and a print list. Let's see how all those work. First, our constructor has 2 attributes. We keep track of the root node and we also keep track of size. So each time we add or remove a node, we're going to increment or decrement the size accordingly. To add a new node, we pass in the data that we want to create that new node with. We create a new node with passing in the data and the next node as the root node. Keep in mind we're inserting this node at the very beginning of the list. So the current root node is going to be the second node. So we pass that in as the next node for this new node. And then we change the root node to the new node. We increment our size by 1 and we're done with the add operation. To find a piece of data, we pass in that piece of data. We are going to iterate through the list, one node at a time. We're going to start at the root node, which we'll call this node. And as long as this node is not none, as long as it's a valid node, we're going to continue to iterate through this list. Each time through this while loop, this else statement is going to bump us forward to the next node if we haven't found what we're looking for yet. So what we're looking for is this node's data is equal to D. And when we find that, we return D. If we get through all the way through the while loop, we haven't found it, we'll return none because that data is not in the list. The remove function, we pass in a piece of data. We need pointers to this node and this node's previous node. So we're going to start iterating through the list to do the find operation at the root, which we'll call this node. And then we're going to keep track of the previous node because we need that to be able to remove the node when we find the one we want to remove. Each time through this while loop, we have two pointers now to increment. We have to increment the previous node to this node, and we have to increment this node to this node's next node. So if we haven't found what we're looking for yet at the end of this while loop, we'll bump forward both of those two pointers. And that's how we iterate through the list. Now our check. We check if this node's data is equal to the D that we were passed in, that we're looking for. If we find it, we found that data, there's two possibilities for removing that node. One, that node is in the root. That's this else here. In which case we just change the pointer for the root node for our linked list to this node's next node. In other words, the second node in the list. We bypass the current root and we point our root pointer to the second node in the list. That effectively deletes the first node in the list. Now if it's not in the root, in other words it's in some other node in the list, then we need to delete that by changing the previous node's next node pointer to this node's next node. So that is the remove operation. If we get all the way through and we haven't found it, we return false. If we do successfully remove it, we return true. And the print operation, we print the list. We're going to iterate through the list, one node at a time starting from the root. This while loop is going to check when we reach the end of the list, and then we're going to exit and just print a none. And for each node, we're going to print the string representation of that node, followed by a little arrow. So you'll see what that looks like when we run the test code in a second. So here's our test code. We test a variety of different operations. Yeah, here's what a list printed looks like. So our string representation of a node is just the value in parentheses, and then we put an arrow between it in our print function. So we'll create a new list called myList. We'll add a few items to it, and then we'll print the list, and you can see what we get here. And then we can print the size of the list. We can see the size is equal to 3. We remove one item, the 8. Then you can see the size is equal to 2. And we can also find the 5. When we find the 5, it actually returns a 5, and we can print that out. And we can also print out the root, which is 12. That's the last item we added, so that's at the front of the list. So that's how the linked list works. So a circular linked list is almost identical to a standard linked list, except that from the very end node, instead of having a none pointer to the next node, it's going to have a loop back to the very beginning, to the root node. The add operation in circular linked lists works slightly differently. Because we have this loop back to the first node from the end node, we'd rather not have to go back and update that every time we insert a new node. So we don't insert the new node as the root node anymore. Now instead we're going to insert it as the second node. We leave the root pointer and the last pointer, the loop back to the root, the same. And instead we insert our new node as the root's next node. And then the next node for our new node is going to be what was previously the second node. So that's the add operation for a circular linked list. So that's basically it. That's the only difference with a circular linked list. So what are the advantages of a circular linked list? Well, it's great for modeling continuously looping data or objects. So something like a Monopoly board or any game board or a racetrack or something that continuously loops. And there are a lot of different looping objects in the real world. So if you want to model some continuously looping set of objects in a computer program, a circular linked list is one way to do that. The circular linked list is very similar to the linked list with a few modifications. In the add method, we have to check whether the list is empty. And if it is, then we add the first node, then we make its next node point to itself. Sounds crazy, but we need to loop back to something. So we loop back to the first node, the root node. Else, if there's already at least one node in the list, we can create a new node and insert it into the number 2 position right after the root and change the root's next node to point to this new node. So that's how the add operation works. We can see the code here, it's only a few lines of code. The find method works exactly the same as in the regular linked list, except that in this elif statement, we have to do a check if we've circled all the way back to the root node again, because if we have to stop our find and return false. We didn't find it. We searched the entire list. We didn't find the value we were looking for, we returned false. For the remove method, let's scroll down here. For the remove method, we need to track both this node and the previous node. So we're going to set pointers for both of those to start out. So we'll start out at the root node and we'll set previous node to none. And you can see towards the end of our while loop here, we advance both of these pointers one node. So they both move forward to the next node. Now we test if we found the data. That's this first if statement. Bingo, found, if we pass this test. And if so, there are two possibilities for the remove function. Number 1, if the previous node is not none, tests whether the data was found in the root node. And if not, the remove is an easy bypass operation for changing the previous node's next pointer, which is what we do here. And case number 2, else, if we need to delete the root, we use this while loop to find the very last node in the list so that we can update its next node to point to the new root because the root has changed. So we find that, we find the last node, we update the last node's new next pointer, which is the new root, and then we update the root pointer itself. Lastly, we decrement the size by 1 and we return true if we successfully remove the data. And in our print list method, we iterate through the list, we print each node followed by an arrow, as you can see, and our while loop has to check if we've made it back to the root so we know when to stop. So this is the test we have here. While this node dot next node is not the root, we continue to iterate through the list. Now let's take a look at the circular linked list test code. Here we create a new circular linked list, we'll just call it CLL. We're going to add a bunch of items to it using a for loop, adding one item at a time. And then we can print the size of the list. We can see down here the result, the size is 5. We try to find an 8. If the value is actually in there, it will return 8. If we try to find an item that's not in the list, it's going to return false. So we can see when we try to find the 12, we get back a false. And instead of using our print list function, here we're going to iterate through continuously so that you can see when we pass by, we're going to print 8 items even though there are only 5 in the list. So we're going to see if it actually does circle back to the next node. We're just going to continuously get the next node up until we reach 8 of them. So we can see 5, 9, 8, 3, 7, and then it starts from the beginning again. 5, 9, 8, 3. It'll continue on. We print up to 8 items. So that shows you that it's a continuous loop and we can continue to loop through that if we want to. Right, a little more test code. We can print the list and here's the current contents of the list and then we remove an 8 and when we print out remove 15 result we see that it's false because there's no 15 in the list. We can see that. And we print the size of the list. Now we have 4 items because we removed 1. We try to remove the 5 node. That completes successfully, and then we print the list again, and we only have 3 items left. So that wraps up this lecture on the circular linked list. Now let's look at doubly linked lists. These are also sometimes called bidirectional linked lists because they have arrows pointing both directions, to the next node and to the previous node. So a regular linked list looks like this. A doubly linked list, each node has 3 pieces of data. It has a pointer to the previous node, a pointer to the next node, and the data itself that it's storing. So it has those 3 things, 3 components to the node of a doubly linked list. So this is what a doubly linked list would look like, a simple one with 3 nodes. We have here a 4, a 23, and a 7. So let's say we want to delete an item. This is a little more complicated because we have 2 pointers to fix, not just 1. So we found this item that we want to delete. We're going to call that this node, and then the previous node to this node is the 4, and the next node is the 7. So how do we delete it? Well, we look at this pointer from the previous node that's pointing to this node. And we look at the pointer from the next node that's pointing to its previous node, right? These ones that are pointing to this node, they have to be fixed. They basically just have to bypass it. So what we do is we change 4's next pointer. Instead of pointing to this, it has to point to this node's next node. And then for 7's previous pointer, instead of pointing to 7's previous node, it has to point to this node's previous node. So we basically do 2 adjustments here. Prev.next equals this.next, and next.prev equals this.prev. So those are the 2 changes that we do to cut this node out of the list. And you see, once we get these red arrows in place, once we fix these 2 pointers, we've effectively cut node 23 out of our linked list. We've deleted it. So that's how the delete operation works in a doubly linked list. Some advantages of the doubly linked list over a standard linked list: you can iterate through the list in either direction. That's pretty obvious. But when you have a really large linked list and you don't want to iterate through all of the items because you happen to know that your item is towards the end of the list, you can actually save quite a lot of time by starting your iteration at the tail end of the list and working your way back. So you could save a pointer to the very end of the list as well. And you can delete a node without iterating through the entire list. That is, if you have a pointer to that node, right? If you know where that node is that you want to delete and you don't have to iterate through the whole list to find it. Each node already stores its previous and next pointer, so you can get the nodes on either side of this node that we want to delete without having to iterate through the entire list, if you have a pointer to the node you want to delete. Doubly linked list uses an extra node attribute called prevNode, as I showed you before when we looked at the node class. And it also has an extra list attribute called last. You can see here, last. So that we can always access the tail end of the list, or the last item in the list. Now the add method has to check if the list is empty. And if so, then the root node is also the last node. So otherwise, it adds a new node to the beginning and it changes the root's prev node to the new root node. So we can see the if-else, 2 different conditions here for the add a new node. The find method works exactly the same as the find method for the standard linked list, so there's really no changes on that. The remove function is a little different. There are 3 possible cases in the remove function. So let's review each one of those. Case number 1, we're trying to delete a middle node. That's this if statement here. So the node is not in either the root or in the last node. That's the standard case that we showed in the slides. So for this, we just do a simple bypass. We bypass the target node, and by changing the previous node's next pointer and the next node's previous pointer, which is exactly what we're doing here. And we've basically bypassed the target node that we're trying to delete. Now the second case is that we're trying to delete the last node. This is just like case 1, except that the previous node's next pointer will be changed to none, because the second to last node is now the last node. So that's the only difference here. So we're changing basically the second to last node's next pointer to none. And the third case is we're trying to delete the root node. And this is again similar to case 1, except that we change the root pointer to point to the second node. In other words, we change root to point to root's next node. And that's it. Those are the three cases for remove. The rest of the remove function is really straightforward. The print list method is pretty much the same. There's no changes there. So let's look at the test code for the doubly linked list. Here we create a doubly linked list, DLL we'll call it. We add a bunch of items using a for loop to add each one of those items in. We can say we print the size is 5. And we can print the entire list if we want using our print list method. And then we can remove an 8. We'll print out the size again. We can see the size is 4. So these things all work. And then if we try to remove items that are not in the list, DLL.remove 15, that doesn't work. If we try to find an item that's not in the list, we also get false back. And if we add some numbers, 21 and 22, and then we remove a 5, and then we print the list again, we can see that 21 and 22 were added to the front of the list, and the 5 was removed. That was a tail node, the last node in the list, and we successfully removed that. And then just for fun, we see that we can print out the last node's previous node, which should be the node right before the 9, which is this 3, which is exactly what it does. So we can access nodes from the tail end of the list also. That wraps up this section on linked lists. So in this section, we covered a standard linked list, a circular linked list, and a doubly linked list, or a bidirectional linked list. We showed you how those work, and then we implemented them in code. And again, I encourage you to download this code and run it and try it out. Make some edits to it, change it, use your own tests on it to see how it works. By using the code, you're going to better understand how the code works, how linked lists work, and how to eventually write your own linked list code, hopefully. In this lecture, we're going to talk about trees. After section 1, where we covered Python's built-in data structures, trees is definitely the next most important section of this course. Trees are a critically important data structure in all programming languages, and let me explain why to make a point. I'm thinking of a number between 1 and 8 million. Can you guess my number? Well, you guess 4 million. I just say wrong. And you're thinking, uh-oh, aren't you going to tell me higher or lower? No. You have to guess until you get my number. Well, you might have to guess every number between 1 and 8 million to figure out which number it is. So if you're using a list, an unsorted list as your data structure, that's what it's like. You would have to iterate through the entire list to find the number. So you may have to do up to 8 million comparisons to locate that number that I'm thinking of. That is the issue with lists. When you have a lot of data, it's really slow to find data. Now with a tree, it's a little different. You guess 4 million, and I say lower. You guess 2 million, I say higher. You guess 3 million, lower. Okay, wow, with 3 guesses, you've shaved off 7 million possibilities, and now you've narrowed down the possibilities to between 2 and 3 million. There are only 1 million possibilities left with just 3 guesses. So with as few as 30 guesses, you would be able to find any piece of data in a tree with up to 10 million nodes. So that is how fast binary search trees are. A balanced binary search tree will let you locate data in a very large tree with as little as 30 comparisons. So now let's take a look at some of the major operations of trees and how they work. So first let's learn some basic terminology about trees. This is a node. Each part of a tree is called a node, and each connection between nodes is called an edge. And at the very top of the tree, we have a root node. You can see that trees are actually upside down compared to real-world trees. This is more like a root system of a tree, or a flipped upside-down tree, or like a management hierarchy in a company or something, right? Where you only have one president and then you have multiple vice presidents and so on down. Trees are great for modeling organizations, but that's not the real benefit of a tree. The real benefit is the speed. Now we have parent nodes and child nodes. In a binary tree, a parent can have up to 2 children, 1 or 2 children. Nodes that have the same parent are called sibling nodes. And bottom nodes at the very bottom of the tree that don't have any children are called leaf nodes. Not all trees are binary trees, but in a binary tree, each node can have up to 2 child nodes, a left and right child node. Now some trees may have 5, 10, up to 1,000 child nodes for each node. We can see that off of 5 here, we have a subtree. A subtree connects to the root node here. And a subtree is basically any part of a tree that in itself is a tree. So 8 can be a subtree of 5. Compared to node 4, 3 and 5 are its ancestors, which is its parent node and every node above the parent in the tree. Descendants are every node below that node in a tree. So node 5's descendant includes everything in its left subtree and everything in its right subtree. In a binary search tree, each node is greater than every node in its left subtree. So here we can see that 15 is greater than every single node in its left subtree. And 8 is greater than every node in its left subtree. And the 5 is greater than every node in its subtree. The 24 is greater than every node in its left subtree. So this is a standard requirement for binary search trees. Each node is greater than every node in its left subtree. And it's also less than each node in its right subtree. Here we can see that all the nodes in 15's right subtree are greater than 15. And all the nodes in 24's right subtree are greater than 24. All the nodes in 8's right subtree are greater than 8. So those are two standard requirements for a binary search tree. Some of the standard operations that all binary search trees are going to use: insert, we want to be able to add new data to the tree. Find, we want to be able to locate data in the tree. Delete is to remove a node. Get size counts all the nodes in a tree to tell us how many pieces of data we have in a tree. And traversals, which enable us to walk through the tree node by node. And I'll show you how some of those work. First, let's look at the insert method. We're going to always start at the root when we're doing an insert. So the top. In this tree, it's the 15. We're always going to insert a new node as a leaf. In other words, at the very bottom of the tree. But we start at the top to locate the right position, the correct position in the tree to insert that new leaf. So let's say we want to insert 12 in this tree. We're going to start out with comparisons starting at the root. Is 12 less than 15? Yes, it is. So we're going to descend down 15's left subtree. Next, we're going to compare 12 to 8. Is 12 less than 8? No, it's not. So we're going to descend down 8's right subtree towards the 11. Is 12 less than 11? No, it's not. And then we compare 12 to 13. And we say, well, yeah, 12 is less than 13. So we're going to add the 12 as a leaf node. So we can add it as 13's left child. That's how the insert function works. Now let's look at the find method. Again, with find, we'll always start at the root. Here it's 15. And we're going to do comparisons. So if we want to find 19 in this tree, we're going to start by comparing 19 to 15. Is 19 less than 15? No, it's greater. So we descend down the right subtree. And then we compare 19 to 24. 19 is less than 24, so we go down 24's left subtree. You can see how with each comparison and decision, we descend down one subtree. That cuts in half the number of remaining possibilities to locate an item. So now we've already, in 2 comparisons, found the 19 in this tree. So when we find a piece of data with the find function, we're always going to return that piece of data. And if we didn't find it, we want to return false to let the user know that data is not existing in the tree. So with delete, there are 3 different possibilities. One is that the node we want to delete is a leaf node. Another possibility is that it has one child node. And there's another possibility that has 2 child nodes. So each one of these we have to handle differently. Delete is a fairly complicated operation. So let's first look at the possibility that the number we want to delete is a leaf node. So look at these gray nodes are all leaf nodes. So in the case of a leaf node, it's easy for us to just delete the leaf node without affecting anything else in the tree. These are bottommost nodes. So it doesn't affect the organization of anything else in the tree. We can just delete that node if it's in a leaf. That's the easiest case right there. Now if we have one child, these are cases where we have one child, node 11, 13, and 28. If we want to delete one of those nodes, we have to promote that child node to the target's node's position. So for instance, if we want to delete the 28, we would promote 25 to 28's position. If we want to delete the 11, we would have to promote the 13 to 11's position. And the 12 comes with it. You're promoting that entire subtree. So that's the one child delete. And then if you have two children, well, that gets a little trickier. Let's say we want to delete the 24, and we can see that 24 has two children. We find the next higher node. In order to do that, we're going to descend down 24's right subtree and then all the way to the left. So here we get to 25. Now if it was a much larger tree, it'd be the same operation. You take the right subtree and then the leftmost node in the right subtree. And here it's 25. So the operation is to basically swap places, the 24 and the 25, and then we can delete the 24. So we put the 25 where the 24 was, and we can delete the 24. And the same thing if we want to delete the 4. Here we want to delete the 4. We can see that 4 has two children. We want to find the next higher node after 4, and we find that's 6. We descend down the right subtree and the leftmost node, and that's 6. So we delete the 4, and we promote the 6 to the 4th position. And the 7 comes with it because 7 is part of 6's subtree. So that's the delete operation in a nutshell. It's actually a little more complicated than that, so we're not going to code it in this video. However, I do have another video on YouTube where we code the entire delete function. Now get size. Sometimes we may want to find out how many nodes are in a tree. So this is a pretty easy operation. The get size function returns the number of nodes, and it works by using recursion. Actually, all of these functions in trees, most of them are recursive. So find, delete, insert, we're doing it recursively because we continue to call the same function using the same parameter until we find the correct position to execute it. So the get size works the same way. The size is equal to 1 plus the size of the left subtree plus the size of the right subtree. In other words, the size of this tree is equal to, well, the 5 node is 1 plus the left subtree is the subtree starting with 3, and then the right subtree is the subtree starting with 8. So we say the size of this tree is 1 plus the size of these two subtrees. And then we'd call the same thing, the same get size function, on 3's left and right subtrees. The size of the 3 subtree is 1 plus the size of 3's left plus the size of 3's right subtrees. So we call recursively the get size function as we descend down the tree, and eventually we get down to leaf nodes and return a 1. Oh yeah, this is a leaf node, size equals 1. And so all those 1s get added back up as we retreat back from the call stack. Now let's talk about traversals. Sometimes we need to traverse the data in a tree, and there are multiple ways of doing that. A few different traversal algorithms are called pre-order traversal, level traversal, in-order traversal, and post-order traversal. So in this video, we're going to cover pre-order and in-order traversal. The pre-order traversal, we visit the root before we visit the root subtrees. So in other words, we're always going to start at the root, and then we'll visit the root subtree. And the same thing here. With node 3, this is basically a subtree starting at node 3. We're going to visit 3 before we visit its subtrees. So we start at the top, and then we descend down the left subtree, and again we descend down the left subtree, and then we hit the right subtree. And then we'll come back up and descend down 5's right subtree. We'll get the left subtree, and then the right subtree. So 1, 2, 3, 4, 5, 6, 7. You can see the order. This is pre-order traversal. An in-order traversal visits the root between visiting the root subtrees. So that means that it can deliver values in sorted order. So here we may want all of these values in sorted order, in which case we're going to start with the bottom leftmost node and work our way up. So 1, 3, 4. We visit the 1's parent node and then its right subtree. And then we visit 3's parent node and then its right subtree, starting with the leftmost node. So we're always, in other words, working our way up from the bottom and working our way to the right. So that's an in-order traversal. What are the advantages of binary search trees? Number one, trees use recursion to implement most of their operations, which makes them pretty easy to implement. Most of the code is pretty easy to write. It's not very complicated. Well, except for the delete, which has a lot of different cases. But the big, huge advantage of binary search trees is speed. They're really, really fast at locating data. You can insert, delete, and find data in a tree in big O of h, or the height of the tree, depending on how many levels there are in a tree. Or, put another way, log n of the data. The log of 10 million is about 30. In other words, if you don't know what big O means, this is an order of operations, an approximation of how many operations it takes to achieve something. So you can do all of these different operations in about the log n of the amount of data you have, which is very fast. So in a balanced binary search tree with 10 million nodes, you can do all of the insert, delete, and find functions in as little as 30 comparisons. That's incredible. That's incredible. So trees are extremely fast. Now let's take a look at how to implement trees. Now let's look at how to implement a tree in Python. So we have this Jupyter notebook running here. We're going to implement a binary search tree. We have a few functions. We have a constructor, an insert, find, and get size method. And then we have two different ways to traverse the tree, pre-order and in-order traversal. And I'll walk you through how all of that code works. So in our constructor, we have three attributes. We have a piece of data that we're going to pass in as a required attribute, and then optionally you can pass in a left subtree and a right subtree. In this program, we're really not using the left and right subtrees in the constructor, so I have them defaulting to none. But each node is its own subtree, and it has a left and right subtree. So the insert function, the key is to find the correct location to insert it, and we're always going to insert it at the very bottom of the tree as a new node. The first possibility is the node that we're in is equal to the data that we're trying to add, in which case we're going to reject that. We don't want any duplicates in our tree. So in this case we're going to return false because we got a duplicate. If the data passed in is less than the data in the current node, then we're going to descend down the left subtree. So we return self.leftSubtree.insert. So in other words, we're calling recursively the insert function, descending down the left subtree and still passing the data along. And the reason we have this return is because we want to return either true or false at the end of the day, if the data was successfully inserted or not. Or if we reach the bottom level of the tree and we found the right position to insert it, we'll create a new subtree with that piece of data, and we'll set it up as the left subtree of its parent node. And we return true because we added that data. Or we can descend down the right subtree. If we descend down the right subtree, again, we're just doing a recursive function call to the insert function. We're passing the data in down the right subtree. And when we reach the bottom of the right subtree, we'll insert a new tree and we'll attach that as the right child of the parent node and then return true. The find function works very similar, except that we don't actually create a new item and insert it. But we recursively descend down to either the left subtree or the right subtree. So if we find that piece of data in the current node that we're in, we'll return that piece of data. If not, we'll do a comparison to the current node to see if we should descend down the left subtree or the right subtree. Now if we reach the bottom of the tree, where we have a none node, we're going to return false. Otherwise, we call the find function recursively on the left subtree, and we pass the data along as the same parameter. And then the same on the right subtree. When we reach the bottom of the right subtree and we didn't find the data yet, in other words, we reach a none node, then we're going to return false because the data is not in the tree. Or, if we didn't reach a none node yet, then we'll continue to descend down the right subtree to find that data. So that's the find function. We basically are just doing a comparison and then descending down either the right or left subtree until we reach the bottom. Get size, like I showed you in the diagrams before. If the node that we're in is not none, then we're going to return 1 plus the size of the left subtree plus the size of the right subtree. So this works recursively. We continue to call get size as we descend down the tree, the left subtree and the right subtree. We add all those together, and we add each one for each node we visit. The preorder traversal checks first if the node that we're in is not none, and if it's not, then we'll print that data, and then we'll continue down the left subtree, calling the preorder traversal function recursively until we reach a none node. And we'll continue down the right subtree recursively until we reach a none node. The in-order traversal is not a whole lot different, and you can see what's different between these two is that we here in the in-order traversal, we have the print statement between those two subtrees. And here the print statement in preorder is before we descend down the two subtrees. So that's really the key difference between preorder and in-order traversals. Now let's take a look at the test code. So in this test code, we're going to create a new tree. We do that using the value of 7 we pass in as a parameter. So now we have a tree with a 7 as the root. We insert a 9 into it, so we have 2 items in the tree. And then we just go through this whole list and add a whole bunch of different items. Oh look, there's a duplicate. So it's not going to add this 9. And we insert each one of those items. Now we're going to print out the tree. For I in range 16, so this will count from 0 through 15, we're going to do a find operation on each one of those numbers. And we can see what it prints out is for 0 it prints false, for 5 it prints false, and for 8 it prints false. But all the rest of them, it returns the number and it prints it out. So you can see that there's no 0, there's no 5, and there's no 8 in this list. So it's unable to find those, it returns a false, and that's what we print. The getSize function returns a 13. So that's the count of the nodes in the tree is 13. And then we do a preorder traversal, we print a blank line, and we do an in-order traversal. And you can see the in-order traversal is exactly the numbers in sorted order. And again, you can see that the 0, the 5, and the 8 are missing in this in-order traversal. So that concludes this lecture on trees. I recommend you to download the code, try it out. Maybe try and code the post-order traversal and try and write some different tests to actually use the tree. Maybe try inserting letters in it or something, or a million numbers and see how fast the tree performs. So another really important data structure is graphs. Graphs are perfect for modeling real-world objects in a lot of cases. A graph consists of vertices and edges connecting those vertices. So, for instance, in a social network, the vertices could be people, right? And the connections are friendships or relationships between people. So there are 2 different types of graphs we can use. Undirected graph, where the relationship is both ways, it's bidirectional. So in this case, in a social network, typically relationships work both ways because both people know each other. So here you can see there are a bunch of vertices and then a bunch of edges between the people who know each other. So an undirected graph is a very common way to model relationships in a social network or connections between a real network where the nodes would be computers and the connections would be cables connecting those computers. Now another type of graph is a directed graph. So if you wanted to model, for instance, airplane flights between cities, well, in some cases there may be a one-way flight or even a round-trip flight, but each leg of that flight is going to be represented by an arrow, in other words, which direction it's going. So if you have a flight going from Chicago to Seattle, well, it doesn't necessarily have a return flight. So the best way to model this is using a directed graph, which shows a one-way relationship. So transportation and networking are just a couple of the very many different possible applications for graphs in modeling real-world problems. So in this section, we're going to cover the 2 most common ways to implement graphs, which is using an adjacency list and an adjacency matrix. An adjacency list stores a list of neighbors for each vertex in the vertex itself. An adjacency matrix stores a 2D array of all of the connections between the vertices in the graph object. So let's take a look at this undirected graph with 5 vertices and a number of edges connecting them. So in an adjacency list implementation, each vertex would store its own list of vertices that it's connected to. So in this case, A is connected to B, C, and E, and that list of neighboring vertices would be stored in node A's neighbor lists. And node B is connected to vertices A and C, and that would be stored in node B's
list of neighbors. Now, using the same undirected graph, we could implement this using an adjacency matrix. An adjacency matrix has all the from vertices and to vertices, and it puts a 0 where there's no edge and a 1 where there's an edge. So here we can see from A to B there is an edge. Now, since this is an undirected graph, this is a mirror image across the diagonal, as you might expect. So if edge A connects to B, then B also connects to A. And this 2D matrix would be stored in the graph object itself, so each vertex doesn't have to remember its own neighbors. Now, if you have weighted edges, it's much easier to implement this with an adjacency matrix. Why? Because instead of putting just a 1, you can put the weight in the matrix. In an adjacency list, you'd have to probably put a tuple, which includes the weight. In a directed graph, it's fairly easy to implement in either one of these. So in an adjacency list, you would just put the outbound edges from each vertex. So from A, you can see that A has an outbound edge to C. So we would list in A's adjacency list only node C. And the directed graph in an adjacency matrix is similar. It's not going to be symmetrical across the diagonal anymore, because B connects to A, but A does not connect directly to B. So we can see that we have B to A as a 1, but A to B is a 0. Which implementation is better? Well, first let's look at two different types of graphs. In a dense graph, every vertex may be connected to every other vertex in the graph. In that kind of graph, there are a lot of edges relative to the number of vertices. So maybe each vertex is connected to every other vertex in the graph, in which case the number of edges would be equal to the number of vertices squared. In a sparse graph, there are relatively few edges, or maybe approximately similar to the number of vertices. So an adjacency matrix takes up v squared space regardless of how dense the graph is. So because we have a list of vertices along the x-axis and along the y-axis of this matrix, it takes up v squared space for the matrix. So a matrix for a graph with about 10,000 vertices would take up at least 100 megabytes. So some trade-offs. An adjacency list is faster and uses less space for a really sparse graph. But the con is that it's slower for dense graphs, because for dense graphs it would have to iterate through all of the neighbors. And an adjacency matrix is faster for dense graphs because it can easily look things up using an index. It's also simpler for weighted edges. It's very easy to implement weighted edges. But the con is that it uses a lot of space. So as the number of vertices grows, the amount of space required for the adjacency matrix grows by a factor of v squared. Next, we're going to learn how to implement each of these methods in Python. Now let's look at the code. I'll post the code on my GitHub site, both in a Jupyter Notebook format, which we're going to walk through in this video, as well as the regular Python file. So you can download that and test it in whichever format you prefer and try it out, and I strongly recommend you do that so you can really understand how graphs work. Now in the code we basically have two classes. We have a vertex class, which is pretty simple and there's not a whole lot to it. And then we have the graph class, which is a little bit more substance to it, but we'll walk through exactly how everything works. And then we have a little bit of test code, and I'll show you how that works. So first let's look at the vertex class. We have two different methods here. We have a constructor. This init is just a constructor that creates a new vertex. And basically it just sets two different attributes for a vertex object. You can pass in the name in, which is the name of the vertex, which for us is just a single letter. And then it assigns it to this name attribute for the vertex. And then it also creates an empty set for the neighbors for that vertex. And then add neighbors. You can pass in the name of a vertex, not the vertex object, but the name of a vertex. It adds that to the neighbors set for that vertex. And remember, sets don't store duplicates. If that neighbor has already been added to the vertex, it doesn't matter. It won't be added a second time. Now let's look at the graph class, which is a little more complex. So we have a few different methods here. First, each graph object stores a vertices dictionary of all of the vertices.
And that is in the format of name, vertex name, and then vertex object. So you can always access from the vertex name, you can always access the vertex object through the dictionary. And when we add a vertex, we pass in that vertex. We check if the object passed in is actually a vertex object, and if the name is in the vertex list yet, and if it's already in that dictionary, then we're obviously not going to add it a second time. And then if it's not, then we'll add that vertex to the vertex dictionary and return true. Otherwise, we return false, which says the add was unsuccessful. And to add an edge, each time we create a new edge, we check if both of the vertices are actually existing real vertices in the graph, because if the vertex does not exist in that graph, we can't add an edge connecting that vertex. And assuming that both vertices are valid vertices, then we add U to V's neighbor list and V to U's neighbor list. That's why we have two different add operations here. And we return true. And then to print the graph, we're really just going to print out the neighbor list for each vertex. So the name of the vertex and then that vertex's neighbor list. And our test code, well, we'll create a new graph G here. And then there are a few different ways to add vertices to that graph. Here's 3 different ways. So we can create a new vertex A by passing into the vertex constructor the name of vertex A. And then we can add vertex A using the add vertex method. Another way is we can do this both of those steps in one operation using just add vertex and then create a new vertex called vertex B. And then we could also use a for loop if we want to add a whole series of vertices. Here A through K, we have to use OR to get the numerical equivalent of A so that we can iterate through those using the range function. And then we convert that back into a letter using CHR, the character equivalent of that number. So there's 3 different ways there that we can add vertices to our graph, and we did all 3. And we don't have to worry about duplicates because we checked for duplicates in our add vertex function. And then in adding edges, well, I just created a list of edges here. Basically, a list consists of 2 letters, which is the 2 vertices that edge connects to. And then we iterate through those and we add edge with the first letter and the second letter, passing those 2 in. And lastly, we print the graph. So now we have a graph with a bunch of vertices and a bunch of edges. What does that graph look like? Well, our print function doesn't really visualize the graph, but it does show us what the adjacency lists look like. Look, the adjacency list for A looks like this. It has neighbors B and E. And B has neighbors A and F. C has just a neighbor G. So, and if you take a look at the edges list, you can figure that out too, right? A has an edge to B and E, right? And so you see B and E in A's neighbor list. But you're also going to see A in E's neighbor list. So if we look down to E, yep, sure enough, there's A. So that's how an adjacency lists implementation works in code. And again, you can download the code and run this and try it out. Spend a little more time getting acquainted with it. How about that? In this implementation of graphs, we use strings, lists, sets, and dictionaries. 4 data structures that we covered in section 1 of this course. In the next lecture, we're going to learn how to implement graphs using adjacency matrix. In this lecture, we're going to look at how graphs can be implemented using the adjacency matrix method. So we walked through how the adjacency matrix works. Let's look at the code. Again, this code is posted on my GitHub site, both in a Python file and in a Jupyter Notebook file. You're welcome to download either one. This code I'm going to show here is the Jupyter Notebook. It has a lot of comments in it. So first we have a vertex class. The vertex class is extremely simple in the matrix implementation because the matrix is basically in the graph class. So the vertex class really doesn't have to do anything. We have a constructor where we simply pass in the name of the vertex. So we assign that passed in name to a single attribute called name, and that's it. That's all a vertex has is a name. The graph class is a little more complicated. We have 3 key attributes here. We have a dictionary of vertices, and then we have a matrix of edges. This is actually going to be a 2-dimensional list of edges. And then we have edge indices, because the edges are unlabeled. All it is a series of 0s and 1s. So this is basically the labels that goes with the edges. So this is not the only way to implement this. This is how I chose to do it. You can implement it different way if you want, if you find this too complicated. So we're going to have a few different functions here, or methods, that are part of the graph class. We're going to add vertex, which is going to update all three of these attributes. We're going to add an edge, which only really needs to update the edges matrix. And then we have a print function. When we add a vertex, we pass in that vertex. First, we're going to verify that that's a valid vertex object and that it's not already in the vertices list. And if it's not, then we'll go ahead and add it. So the first step is to update the vertices dictionary by adding the name and vertex to that dictionary. So in other words, we'll have A and then the vertex object A. Next, we're going to use a loop to append a column to the rightmost side of that matrix. So the edges matrix. So we use a for loop to do that. And we append a column of zeros to the rightmost end of the edges matrix. And then we need to put on the very bottom of the matrix, we need to append a row of zeros on the very bottom. So we do that using the self.edges.append 0 times length of edges plus 1. In other words, however many edges there are, we're going to add a 0 at the very bottom row for each one of those. Now, since we just added a vertex, there's obviously no edges connecting to it yet, so we know these are all zeros. But as we add edges connecting to that vertex, then we're going to flip them to a 1. And the last step in adding a vertex is we update the edge vertices. We add that vertex name and the index that we can find that vertex at in the edges list. And when we add an edge, we pass in u and v, which is the from and to vertices for the edge. We have a default weight of 1. That's normal to have a default weight of 1, but you can override that by passing in whatever weight you want. So if you want to use weighted edges, it's pretty easy to do. We check to make sure that both vertices that we passed in are valid vertex names. In other words, they're actually in the vertices dictionary. So edges is a two-dimensional list. So we need two different indices to access a specific position in the matrix. So we have a u and a v, and then we have a v and a u. So we want to flip both of those for edges, those two positions in this table, set it equal to weight, whatever weight you passed in, or 1 if this is the default. And lastly, when we print a graph, well, you'll see how it prints out down below. But we're starting out by printing the name of the vertex, and then we're going to print out the row of 1s and 0s for that vertex. So our test code, we used exactly the same test code that we used for the other implementation of the graph, using adjacency lists. The test code is identical. So we create a new graph. We have 3 different ways of adding a vertex to the graph. First, for A, we create a new vertex object, and then we do add vertex A. And then for B, we add vertex, and we create a new vertex inside the parentheses here. And then we use the for loop method where we iterate through the A through K and we add them to the graph. And then to add an edge, I created a list of edges here. This is the same list we used in the other test code. For edge and edges, in other words, we're iterating through those edges. We add each edge one at a time. We pass into the add edge method 2 parameters. In this case, it would be the A and the B. So we're getting the left character and the right character. We're passing those in as the attributes. And then when we print out the graph, we see what this looks like. This is what our neighbors matrix looks like at the end of this. So you can see where we have a 1 is a neighbor for A. So this would be B, C, D, E. So B and E are A's neighbors, right? Wherever there's a 1. And then this is column A. So we can see that A has an edge to B and E. So in other words, you can see that it's symmetrical across this diagonal. And every place where there's a 1 reflects an edge between 2 vertices. So I recommend you download the code, test it out, try to use it and get familiar with it. These are 2 different implementations for graphs, and it's important to understand both because there is no one best method, as I already explained. In different instances, each method has its advantages. In this course, we've covered a lot of different data structures. We've learned how to use different data structures as well as how to implement and some of the pros and cons of each. Now you'll have a lot of new tools in your tool belt as a programmer to solve problems as you're developing code. Thank you for taking this course.